Let's look at a couple of examples where we apply the two-way ANOVA method. It says a researcher is interested in investigating how teaching methods and class size affect student engagement in a college course. As you can see, teaching methods has two values or two groups, traditional versus collaborative, and class size also has two groups, small versus large. So that means we have two categorical variables, and we want to see how they impact or affect student engagement, which is a quantitative variable that's on a scale from 1 to 10. What we want to do is test whether teaching method and class size affect student engagement using alpha equal 0.05, our significance level. So the research question here is basically given in that last sentence of the previous column of information. But when I see this, I actually see three different questions that we could possibly answer with the two-way ANOVA. Does teaching method have a significant effect on student engagement? Does class size have a significant effect on student engagement? And is there an interaction between those two variables on impacting student engagement? And so let's see how we can potentially test for each of those questions, right? Well, one, this last question, remember, requires that we have replicates in the combinations of groups that are made by those two categorical variables. And so I have my data listed here, but let's open up the data set in JASP to see if there are more than one observation in each of the combinations of groups, right? So I have JASP here, and I'm going to open our data set by going to browsing in my computer. This is example 5 of the two-way ANOVA. And so if you look here, I have each of the students in my study are on a separate line in my data set. This first student is in the traditional teaching method in a small class size. That's their engagement score. The second student, same class in teaching method. This is their engagement score. Notice that I have some students that are in the traditional classroom method, but in a large class. I have some students that are in the collaborative teaching method in the small class size, and then some students that are in the collaborative with the large class size, right? So I have replicates in each combination of the groups, which means I am going to be able to test for an interaction effect. So I can respond to each of those research questions that were given on that previous slide in our notes. So I'm going to write the null and alternative hypothesis for each of these hypothesis tests. And you're going to see that I'm writing these slightly different than I've done when I've looked at the one-way ANOVA. Remember I said that when I look at just the single variables, they are main effects. And then when I look at the interaction, those are interaction effects. So what I'm doing in these null and alternative hypotheses is seeing if the grouping variables have an effect or a significant effect or not in the population. And I'm also looking at whether the interaction effect is significant in the population. So my first test is related to teaching method. My null hypothesis is that there is no significant effect of teaching method on student engagement in the population. I have population abbreviated with POP here. And then the alternative is that there is a significant effect of teaching method on student engagement. All right, I can write my second null and alternative hypothesis in a similar way, and I can do a similar thing for the interaction. My null for the interaction effect is that there is no significant interaction between class size and teaching method on student engagement in the population. And of course, my alternative is that there is. And so again, we're going to go through the process of using JASP to conduct each of those tests. Before we conduct the test, we want to check the assumptions, and we also want to get some descriptive statistics. And so let's talk about the assumptions. Of course, we're assuming independent groups. There are, in much the same way as we had independent groups, and we used the independent t-test, and when we did not have independent groups, we used matched pairs or the pair sample t-test. The same thing is going to happen for the one-way and two-way ANOVA. There is another ANOVA for when our observations are not independent. Unfortunately, we're not going to get to that in this course. You will get there in your next statistics course. So all of the examples that we're going to deal with are going to have independent observations. But that's basically satisfied by research design. We can check, however, the normality and the homogeneity of variance assumption. With the normality assumption, we need that our residuals or our errors are normally distributed by all combinations of the factors. We can test this by doing a QQ plot of residuals. I'll show you that in JASP. If our normality assumption fails, meaning I don't see a scatter plot where most of the points are near that line, then we're going to have to use a non-parametric test. We're not going to run through a non-parametric test in this course, but I will show you what that non-parametric test is called and where you can access it in JASP when we go a little later. We also have the homogeneity of variance assumption. I use this term here, homoscedasticity. That is a term that's used in the regression framework. Actually, these residuals are basically following from the regression framework. We're not going to learn about regression until our next module. And so I know I'm using some of these terms before they're getting introduced, and I do apologize for that. But it'll become a little clearer during our next lecture. But homoscedasticity is the regression equivalence of homogeneity of variance. We're studying this stuff from the framework of ANOVA, but JASP sometimes uses different terminology, or I just want you to know the terminology in case you search online for some of these topics. You'll see things, and you can make the connection. We're going to use Levine's test to test for this homogeneity of variance, which is the same thing that we did with the one-way ANOVA and the two-sample t-test. If the test is significant, we're going to use Welch's ANOVA. That means we get a p-value less than 0.05 when we do Levine's test. Now, although I'm going to show you how to check your assumptions in this course, we're not going to have any examples where these assumptions are not satisfied, because JASP does not have the capability or the capacity to run Welch's test when we have more than one factor. So we won't see an example where we'll fail the homogeneity of variance. Or if we do, we'll cautiously use our regular two-way ANOVA method and just make a note that our homogeneity of variance assumption was not met, and so we'll proceed with caution when interpreting those results. All right, let's go to JASP and actually run these assumption checks. So I've already uploaded my data as we've discussed before. Remember, we can go to this ANOVA module here. Under the classical menu, I'm going to select ANOVA. Our dependent variable is our quantitative variable, right? That's what those are the means that we're interested in comparing. And then our factors are going to be in this fixed factors box. Now, when I do that, my ANOVA results are going to appear here. But before we get there, let's go ahead and check our assumptions. There's a section here called assumption checks. So I'm going to go here. I'm going to select homogeneity tests. That's where we have Levine's test. And then I'm going to also get the QQ plot of residuals. While the QQ plot of residuals is opening, notice here my Levine's test is not significant. Our p-value is greater than 0.05. So we can move forward assuming that we have homogeneity of variance. If I look at my normal QQ plot, most of my points on my scatter plot are near this line here. And so we have evidence that our data are normally distributed. Had this not been normally distributed, we would have to use a non-parametric test. Non-parametric test, if you go to this menu here, is to the bottom. The test is called the Kruskal-Wallis test. Kruskal-Wallis test. You would put your values here for your two factors. You can get an effect size measure. You can do post hoc tests, so on and so forth. But that is what we get when we do Kruskal-Wallis, if our normality assumption is not met. But ours is met. And so we could actually move forward using JASP as we normally would. By the way, right now, there's some homogeneity corrections. None is selected. If you were to try to select Welch, you're going to see that these are only available for one-way ANOVA. So that is why we're not going to go through the process of interpreting when our equal variances or homogeneity of variance assumption is not satisfied. But if you had statistical software that could do it, you would interpret it in the same manner. All right, so our assumptions are met. And so now what we want to do is we want to get some descriptive statistics, right? So one of the descriptive statistics that we're going to be interested in are the means of each of the groups and combinations of the groups, right? So under this display section, I just selected descriptives. And as you can see here, I have a table that has sample size, mean, standard deviation, so on and so forth for the combinations of the groups in my data set. On the first row, I have information for the collaborative large class size group. The second row has the collaborative small classroom group. The third row, traditional large classroom. And then the last row, traditional small classroom. Each of the groups have a sample size of 10, and the means range from 6 to about 8, right? With a small standard deviation. Now, you can draw some conclusions about your sample. Right? Using this table. But it may be slightly easier to go to descriptives plots to get an example of a graph where you can draw conclusions about your sample based off of this information in this chart, right? So what I'm going to do is on the horizontal axis, I'm going to put the teaching method. And on the separate lines, I'm going to put the class size. It doesn't matter which variable you choose. You're just going to get a different looking graph, but you can still draw the same conclusions. Notice here on my horizontal axis, our values of our teaching method are overlapping. Notice since I'm selected here, I see this little triangle. I'm going to widen this so that there's no overlap here. And now I can get a better sense of what I see on my graph. Now, remember, our goal is to conduct three tests, 2 of the main effects, and then 1 of the interaction, right? This is an interaction plot, but I can get information about all 3 of these tests by looking at this sample data. Now, it's not going to tell me the results of the test because I need to get my F statistic and my p-value to really know the results of that test. But it could tell me what's going on in my sample to help me see what evidence I see in my sample that may be related to those test results, right? So one of these lines, with the ones with the open endpoints, represent large sample sizes, and the one with closed endpoints represent small class sizes, right? I can see that since the small class size lines are above the large classroom lines, there looks to be a significant difference. I'm not sure if it's significant, but there is a difference in the performance in terms of engagement score between small class sizes and large class sizes, with smaller class sizes being more engaged, right? That's looking at just that variable. Now I'm going to look at the collaborative versus traditional. Well, whether you're in a small or a large classroom, the collaborative group endpoints are higher than the traditional classroom endpoints, right? When I look at the small classroom, collaborative is higher than traditional. And when I look at the large classroom, collaborative is higher than traditional. That's some evidence that teaching method may be significantly different. I don't know. At least I know it's different, significantly different. That is for the hypothesis test. And then, so those are the main effects, right? Now, looking at the interaction, I look at whether the lines are parallel or whether they're non parallel or skewed. These lines look approximately parallel, right, in our sample. That's evidence that we do not have an interaction effect. All right. Again, this is based off of sample information. Let's look at the hypothesis test to determine whether we can draw conclusions about what we expect in the population, i.e., significance. So these are those ANOVA results. And in JASP, that was the first table that appeared. And so that's already there. So let's look at each of those tests. The p-value for the main effect of teaching method, the p-value is less than 0.01. That's less than 0.05. So we're definitely going to reject the null hypothesis. There is sufficient evidence to conclude that there's a significant effect of teaching method on student engagement in the population. So that's evidence that the population means for collaborative versus traditional are significantly different. When we look at our second main effect, class size, our p-value here is less than 0.01. So that means we do have sufficient evidence to say that the population mean for a large class size is significantly different from the population mean for a small class size, right? Here, I say there's sufficient evidence to conclude that there is a significant effect of class size on student engagement in the population. And then last but not least, this third row, FYI, this is how we usually write interaction effects. We have the first factor crossed with the second factor. Or in other words, the first factor times the second factor, right? The p-value for that interaction effect is 0.446. That is actually greater than a significance level of 0.05. So in this case, we do not have enough evidence to reject the null hypothesis. There's not enough evidence to conclude that we do have a significant effect of those two variables on our output variable. All right. So those are the results. Our main effects are significant. Our interaction effect is not. While that is the case, we can still, since we do have some significant results, and whether we had it or not, we could get a measure of effect size for each of our effects, our main effects and our interaction effect. And then we can talk about the proportion or percentage of variance that's explained versus not explained with this two-way ANOVA. So we get an effect size measure for our teaching method, right? So the proportion of variance that's explained by teaching method is given by our eta squared. By the way, I didn't show you this in JASP. So let's go back to JASP. And I want to add the effect size measure eta squared to this ANOVA chart. So under the display section here, I'm going to check estimates of effect size, and I'm going to select eta squared, and then we'll see that eta squared is added to that chart there. So the variance explained by teaching method is that 0.523. The variance explained by the class size is 0.336. Both of those are large effects. And the variance explained by the interaction term is small, is 0.002. So we're explaining, if I add up those three values, 0.861 or 86.1% of the variance in student engagement scores. And so had we just looked at teaching method, for instance, we would only be able to explain 52.3% of the variance. However, by adding class size as another variable that can explain variance, we're explaining a lot of the variance in those student engagement scores by adding that additional variable. Well, if we have 86.1% of variance that is explained, If I do 100 minus that 86.1%, we'll see that we have 13.9% of the variance that's left unexplained. All right. So that is those are the results from this analysis of variance here. Let's look at another example. It says an educational researcher is examining how study environment and self-efficacy influence student performance on a standardized test. There are three study environments: quiet, moderate noise, and high noise. And then there's three self-efficacy levels: low, medium, and high. Those are our two categorical variables, probably going to be two factors. And then our outcome variable, our quantitative variable, is a score on a scale from 0 to 100 on a standardized test. What we want to do is determine how study environment and self-efficacy influence students' test scores. And if there is an interaction between these two factors, and we're going to use significance level of 0.05. Well, since I have two factors, one quantitative variable, I know I'm going to have three tests. Test one is about study environment. There is no significant effect of study environment on student performance. Test two is on self-efficacy. Those are our hypotheses there. And then test three is about the interaction. All right. I'm going to go to JASP and I'm going to select new here. And I'm going to get a new window so that I can do another analysis. So this is example 6. And I want to see whether I have replication here. All right. So I have my study environment variable in the second column here, my self-efficacy variable here. I have a student ID variable. That's an ID variable. And then I have the test scores. And so what I'm going to do first, I'm going to go to ANOVA. Notice here how this menu opened up this way. I'm going to slide this to the left. And I'm just going to run through these analyses really quickly. I know that my test score is my dependent variable, my self-efficacy, and my study environment are my factors. So I have two factors here. And I'm going to get my descriptive statistics. And I'm going to create a plot where I put my environment on the horizontal axis and self-efficacy on the separate lines. Notice here I have this wide or narrow axis with the values overlapping. I'm going to widen that. Okay. These are my descriptives. I'm going to come back to that. We also want to do some assumption checks. I have my homogeneity tests, and I'm going to do my QQ plot of residuals. All right. This is insignificant, so I have a homogeneity of variance, and then most of these lie on the line, so I have my normality assumption satisfied, right? As I can see, I have no parallel lines. All right, none of them are completely parallel. In fact, I see some interaction evidence here. They're not all parallel. I also see that this line for the high self-efficacy group, the test scores in the sample are all higher than the mean test scores for all of the other groups, right? That's evidence that self-efficacy may be a significant main effect. And since these noise environments are not all at the same level, there may be a significant effect of study environment as well. All right. I'm going to go and interpret my results, and I'm going to actually go ahead and add my eta squared. And that way I'll have everything I need to draw conclusions about this data set. All right. So if I go back to my notes, homogeneity of variance and normality all check out. I have my descriptives. These are the results of my hypothesis test, right? Notice for study environment, it's on the first row of my two-way ANOVA table. I have a significant p-value, so I do have sufficient evidence to reject the null and conclude that the study environment significantly affects student performance in the population. Same thing happens for self-efficacy and for interaction, right? My interaction term is study environment crossed with self-efficacy. My p-value is less than 0.001. There is sufficient evidence to conclude that there is a significant interaction between these two variables. I can explain my variance by looking at my eta squared, right? So 0.434 is the proportion of variance explained by study environment. 0.355 is the proportion of variance that's explained by class size. And then my interaction term explains about 0.037, that proportion. If I add those together, I get 82.6% of the variance in this model is explained by the model. 100 minus 82.6% is 17.4% of the variance being unexplained by this model. All right. So we're explaining the vast majority of the differences in student performance on that exam by including the interaction term, student environment, and class size. All right. So you're kind of getting a rhythm as to how we can interpret results based off of these two examples here. In both of these examples, we saw data where we had replicates in each combination or in each group combination, right? There are cases where you won't see this. And so I did want to give you one example of that. We're not going to go through the full example, but I want you to see an example where there's no interaction effect possible. It says a school district wishes to study the driving times of a small group of homebound teachers on various routes from one location to another. Using the 5% significance level, do teachers' driving times vary between teacher or route? So this is what this data up here or looks like. I'm going to go to JASP. I'm going to create a new window. And this is example 7. And I just want you to look at this example here. So I have 1, 2, 3, 4, 5 teachers, Blair, I guess it's the last name, Blair to Warren. One of the routes those teachers are driving are I-385. We have their drive times. I have the same 5 teachers, but now they're driving in Main Street or on Main Street route. The same 5 teachers are again going to drive, but they're on the Haywood Road route. And then I have those same 5 teachers once again on the East North Street route. And I have their driving times. So notice here, I only have one combination, one individual with the combination Blair and I-385. I only have one observation with the combination Gene and I-385. Since I don't have any other individuals with that combination, I don't have replication in my study, in my combinations of groups. When that is the case, and I want to do a two-way ANOVA, right? I'll just do it here. No, I want you to see what happens. I'm going to put travel time in my dependent variable. That's our quantitative variable, right? And then I'm going to take these two and put them in the fixed factors box. Notice here it says an error occurred while computing the ANOVA. Residual degrees of freedom equals 0. When we don't have replication, we don't have enough sample size to actually estimate everything. All right. And so what we have to do is we have to remove the interaction term because we don't have enough available information to actually do all the estimates we need. And so in order to do that, if I go here to the section that says model, this section is actually populating as soon as we start adding stuff up here. The only time I haven't mentioned it before because it really didn't matter so far, but now it matters. This model tells JASP what rows to include in our model, which are going to appear in that ANOVA table. Right now, we're going to have a row for driver, a row for route, and a row for the interaction term driver times route, and then, of course, the residuals. Well, since we don't have enough degrees of freedom or the sample size isn't enough for us to estimate anything about the interaction, we need to remove the interaction term. So one way to do that is to just click on driver times route and click this menu or this arrow to the left here. And then now we're going to have all of our ANOVA estimates now available. So if you ever get into a case where you don't have any replication, or even if you didn't look at your data to see if there was replication in each combination of groups, if you get that error when you're trying to do a two-way ANOVA, make sure you remove the interaction term from that model, and you'll be able to estimate your two-way ANOVA that way. All right? And so I'm going to stop here. The interpretations are going to be very similar as the interpretations from before. And so I'm going to stop here with this example. I think you have enough information to do all of the practice problems that you will see for the week. So do the practice problems, and if you have any issues or anything like that, please let me know. I'll see you. This concludes the last video for this module. I'll see you in our next module.